Hi there! I'm very curious about these matter I found. Some look sharp and some look round. What are they? Why do they exist?
Try this out.
That's right. These are rocks and minerals. But do you have any idea how these two are connected? What are the similarities between rocks and minerals? How do they differ? Okay. Earth's crust is the source of a wide variety of minerals, and many of which are useful and essential to people. Most people are familiar with the common use of basic metals, including aluminum in beverage cans, copper in electrical wiring, gold in jewelry, and silicon in computer chips. In addition to that, every process studied by geologists depends in some way on the properties of these basic earth materials. Events such as volcanic eruption, mountain building, weathering and erosion, and even earthquakes involve rocks and minerals. Want to know more about these things? Come and join us as we blast off the rocket ship of new learning. Rocks on Earth may be composed of hundreds of possible minerals, but only 20 to 30 minerals are common in the majority of rocks. Minerals are made up of combinations of nearly 100 different elements, yet only 8 elements make up over 98% of the Earth's crust. We tie the 3 major rock groups together in the rock cycle, a simplified view of the formation of different rocks to illustrate the potential interaction between rock types. Minerals as the building blocks of rocks. Geologists define minerals as any naturally occurring inorganic solids that possess an orderly internal structure and a definite chemical composition. Thus, for any earth material to be considered a mineral, it must exhibit the following characteristics. We have number 1. It must occur naturally. It is a mineral if it has been formed by geologic processes without any human intervention. Number 2. It must be inorganic or was never alive. A mineral is inorganic if it is formed by inorganic processes and does not contain any organic compounds. Number 3. A mineral should be solid. A mineral should exhibit stability at room temperature, which can only be attained if it is solid. Number 4. It must possess an orderly internal structure, that is, its atom must be arranged in a definite pattern. And number 5. It must have a definite chemical composition that may vary within specific limits. Rocks, on the other hand, are more loosely defined. Simply, a rock is any solid mass of mineral or mineral-like matter that occurs naturally as part of our planet. A few rocks are composed of almost entirely of one mineral. A common example is the sedimentary rock, or limestone, which consists of impure masses of the mineral calcite. However, most rocks, like the common rock granite, occur as aggregates of several kinds of minerals. The term aggregates implies that the minerals are joined in such a way that the properties of each mineral are retained. Just a quick trivia. The world's largest rock is called Mount Augustus, which sits in the Golden Outback of Western Australia. Composition and structure of mineral. Each of Earth's nearly 4,000 minerals has a unique substance that is defined by its chemical composition and internal structure. What elements make up a particular mineral? In what pattern are its elements bonded together? Let us have a brief review about the basic building blocks of minerals, which are the chemical element. At present, we have 112 elements that are known, but only 92 are naturally occurring. Some minerals, such as gold and sulfur, are made entirely from one element, but most elements are not stable. Thus, most of them are a combination of two or more elements joined together to form a chemically stable compound.
Hi, this is Teacher Vinch, and now, at this moment, we are going to discuss concept number 3, which is all about the properties of minerals. Minerals occur in a fascinating palette of colors, shapes, and lusters. They vary in hardness and may even have distinctive taste or scent. We will now look at these properties, which are very important or very useful when we identify minerals. So I want you all to listen carefully and write down notes as we discuss this lesson. There are around 8 properties of minerals identified in this module, and there are a lot of activities for you to enjoy, so buckle up and prepare yourself to listen. The first property of a mineral identified in this module is called the crystal form. Crystal form is the external expression of a mineral's internal orderly arrangement of atoms. Generally, when a mineral forms without space restrictions, it will eventually develop into an individual crystal with well-formed crystal faces. As shown here in the picture, the first picture, this is an example of a pyrite. It is an iron and sulfur mineral with a cubic crystals in it. And as shown here in the second figure, this is an example of a distinctive hexagonal crystals of the mineral quartz. This is formed when space and time permit. However, most of the time crystal growth is severely constrained. It is stunted because of the competition for the jammed crystals, none of which exhibits crystal form. This is what happens to the mineral in the granite. Thus, most inorganic solid objects are composed of crystals, but they are not clearly visible to the unaided eye. The second property is identified as luster. Luster is the appearance or quality of light reflected from the surface of the mineral. Minerals that have appearance of metals, regardless of color, are said to have metallic luster, like the pyrite crystal. Minerals with a non-metallic luster are described by various adjectives. These include vitreous or glassy, like the quartz, crystals, pearly, silky, resinous, and earthy or dull. Some minerals appear somewhat metallic in luster and are said to be submetallic. The third property is called color. Although color is an obvious feature of mineral, it is often unreliable in diagnostic property. Slight impurities in a common mineral, like quartz for example, gives it a variety of colors, including pink, purple, or amethyst, milky white, and even black. And the fourth property is called streak. Streak is the color of a mineral in its powdered form, which is much more reliable indication of color. Streak is obtained by rubbing a mineral across a piece of hard unglazed porcelain termed as a streak plate. Whereas the color of a mineral may vary from sample to sample, the streak usually does not, and is therefore the more consistent property of a mineral. Streak can also help distinguish minerals with metallic lusters from those having non-metallic lusters. Metallic minerals generally have dense dark streak, whereas minerals with non-metallic lusters do not. The fifth property is called hardness. One of the most useful diagnostic properties is hardness, a measure of the resistance of a mineral to abrasion or scratching. This property is determined by rubbing the mineral to be identified against another mineral of known hardness. Another mineral will be scratched using this mineral, Geologists use the standard hardness scale called the Mohs scale. Consists of 10 minerals arranged in order, from 10 being the hardest and 1 being the softest. Any mineral of unknown hardness can be rubbed against these 10 minerals to determine its hardness. For example, the fingernail has a hardness of 2.5, and the copper of penny has a hardness of 3.5, and a piece of glass has a hardness of 5.5. The mineral gypsum, which has the hardness of 2, can easily be scratched using the fingernails. Quartz, the second hardest, will be common minerals at 7. To further understand the first 5 properties of minerals, we have here a simulation activity. Please press the first link provided in this description box. Pause this video and proceed in answering the activity. The directions will be given. And once you've finished, please continue this video as we will be discussing the rest of the properties of minerals. Good luck! Yay! It seems like you've finished the activity. How was your experience? Fun, isn't it? Well, we have more as we go through this discussion, so buckle up and prepare yourself. The 6th known property of a mineral is called cleavage. Cleavage is the tendency of a mineral to cleave, or break along planes of weak bondings. Not all minerals have definite planes or weak bondings, but those who possess cleavage can be easily identified by the distinctive smooth surfaces that were produced when minerals are broken. The simplest type of cleavage is exhibited by minerals called micas, the one used for cosmetics. Micas have weak bonds in one direction from the cleave to form thin flat sheets. Please do not confuse with cleavage in crystal form. When a mineral exhibits cleavage, it will break into pieces and have the same geometry as the other. But by contrast, the crystals do not have cleavage. If broken, they are fractured into pieces that do not resemble each other or the original crystal itself. The 7th identified property of a mineral is called the fracture. Fracture is a property of a mineral breaking in more or less random patterns, with no such smooth, planar surfaces. Since nearly all minerals have orderly atomic structure, individual mineral grains have external axes of length, width, or depth, related to the consistent arrangement of the atoms. Minerals that do not exhibit cleavage when broken, such as quartz, are said to be fractured. Even fracturing this variety, minerals that break into smooth curved surfaces, like those seen in broken glass, have a conchoidal fracture. Others breaks into spoilers or fibers, or like asbestos, but most minerals fracture irregularly. The last but not the least property of mineral is referred to as the specific gravity. Specific gravity compares the weight of a mineral to the weight of an equal volume of water. For example, if a cubic centimeter of water, its specific gravity is 3. With a little practice, we can estimate the specific gravity of minerals by hefting them in your hand. For instance, a mineral feels heavy as a common rock you've handled. So, its specific gravity would probably be somewhere between 2. Some metallic minerals have specific gravity noticeably greater than the common rock-forming minerals. Galena, which are ore or flead, has a specific gravity of roughly 7.5. The specific gravity of a pure 24-karat gold is known to be hefty 20. In summary, a number of special physical and chemical properties are useful in identifying particular minerals. This includes taste, the smell, the elasticity, malleability, the feels, the magnetism, double refraction, and the chemical reaction to hydraulic acid. Remember that in every one of these properties depends on the composition of the mineral and its structure, or how your atoms are arranged.
The rock cycle. Many things can happen to a rock after it forms. It can break apart or be buried deeply and melt. The rock cycle is the interactions among the numerous components and processes of the Earth system. It shows three types of rock. First is igneous, second is metamorphic, and third is sedimentary, and the processes that forms them. The cycle starts with the molten rock called magma, which forms by melting that occurs primarily within Earth's crust and upper mantle. Once formed, a magma body often rises towards the surface because it is less dense than the surrounding rock. Occasionally, magma reaches Earth's surface where it erupts as lava. As magma cools, either at depth or after being erupted into the surface, it will solidify and harden, a process called solidification. Molten rock may solidify either beneath the surface or at the surface during volcanic eruption. Resulting rocks are called igneous rocks. If igneous rocks on the surface interacts with sunlight, rain, wind, plants, and animals, as a result, it may be mechanically broken or altered by chemical reactions. They undergo weathering. The daily influences of the atmosphere slowly disintegrate and decompose. Rocks can be stripped away by erosion and moved away from their source. Glaciers, flowing water, wind, and the force of gravity on hill slopes can transport eroded material away from where it is originated. Eventually, these particles and dissolved substances called sediment are deposited. Although most sediment ultimately comes to rest in the ocean, other sites of deposition, river like floodplains, desert basins, lakes, inland seas, and sand dunes. Once deposited, sediment can be buried and compacted by the weight of overlying material. Chemicals in groundwater can coat sedimentary grains with minerals and deposit natural cements that bind adjacent grains. Eventually, these particles and dissolved substances called sediment are deposited. Although most sediment ultimately comes to rest in the ocean, other sites of deposition, river like floodplains, desert basins, lakes, inland seas, and sand dunes. Once deposited, sediment can be buried and compacted by the weight of overlying material. Chemicals in groundwater can coat sedimentary grains with minerals and deposit natural cements that bind adjacent grains. The process of sediment turning into rock is lithification. The sediments undergo lithification, a term meaning conversion into a rock. Sediment is usually lithified into sedimentary rock when compacted by the weight of overlying materials, or when cemented as checkpoint. If the resulting sedimentary rock becomes deeply buried or is involved in the dynamics of mountain building, it will be subjected to a great pressure and intense heat. The sedimentary rock may react to the changing environment by turning into metamorphic rock. If the metamorphic rock is exposed to high temperatures, it will melt to produce a magma. Melting usually occurs at great depth, in the lower crust or the mantle, and the cycle begins again. Alternatively, igneous rocks may remain at depth, where the high temperatures and forces associated with the mountain building may metamorphose or even melt them. At any point during its history, a rock may be uplifted back to the surface where it is again exposing the once buried rock. When this happens, the material turned into a new raw materials for sedimentary rocks. Over time, rocks may be transformed into any other rock type, or even into a different form of the original type. Rocks may take many paths through the rock cycle. Igneous rocks means ignis means fire are formed when magma or lava cools and crystallizes. Magma is a molten rock that is most generated by melting rocks in Earth's mantle. Occasionally, molten rock reaches the Earth's surface where it is called lava. Basically, igneous rocks formed into two basic settings. Molten rock may crystallize within Earth's crust over a range of depths, or it may solidify at Earth's surface. When molten rock solidifies at the surface, the resulting igneous rocks are classified as extrusive or volcanic, while igneous rocks that form at depth are termed intrusive. Igneous rocks vary from nearly white to nearly black, or they can have mixed colors. They may contain holes, fragments, or ash that has been compacted. Intrusive and extrusive igneous rocks differ from each other not only in where they form but also in the size of their crystals or grains. The rate of cooling strongly influences crystal size. If magma cools very slowly, the ions can migrate over great distances, results in the formation of fewer larger crystals. On the other hand, if cooling occurs rapidly, the ions lose their motion and quickly combine. Igneous rocks are divided into two groups, intrusive and extrusive, depending upon where the molten rock solidifies. Intrusive rocks commonly have large mineral crystals because of the slow loss of heat. Intrusive rocks form at depth and they are surrounded by other rocks. It takes a long time for them to cool. Extrusive igneous rocks, on the other hand, are composed of small minerals that cannot be seen by the naked eyes because of the rapid cooling. Extrusive igneous rocks are formed as lava and cools on the surface of the earth. The quick cooling rate keeps mineral grains from growing large. Because the atoms in the liquids don't have the time to arrange into large crystals, the above-mentioned process is called crystallization, which cooling reverses the events of melting. Geologists identify igneous rocks as on the basis of their texture and mineral composition. The several igneous textures describe mainly from different cooling histories where areas the mineral composition of an igneous rock depends on the chemical makeup of its parent magma. Since igneous rocks are classified on the basis of both mineral composition and texture, some rocks having similar mineral constituents but exhibiting different textures are given different names. Igneous rocks can be divided into four categories. First, based on their chemical composition. First is the felsic, second is intermediate, third is mafic, and fourth is ultramafic. Felsic rocks are igneous rocks that are rich in feldspar and silicon. The word felsic was made from the parts of those words because they are made of lighter elements. They tend to be more buoyant than mafic rocks, which are rock high in magnesium and iron like basalt. Intermediate rocks are roughly even mixtures of felsic minerals. There is little or no quartz. Felsic rocks are mostly feldspar, at least 10% quartz, and less than 15% mafic minerals. Mafic rock in geology are rocks that is dominated by the silicates pyroxene, amphibole, olivine, and mica. These minerals are high in magnesium and ferric oxides, and their presence gives mafic rock its characteristic dark color. An igneous rock with extremely low silica composition, being made of almost all olivine and pyroxene, is called ultramafic rocks. It contains a very low amount of silica and are common in the mantle. Primarily, ultramafic rocks are comatite and periodicite. So here we have an example of the classification of an igneous rocks. So for felsic is we have granite, for intermediate is we have diorite, and for mafic we have gabbro basalt, and for ultramafic is we have dunite.
Hello everyone, again, I am your teacher Rose, and now I will take the floor to continue our lesson about the 3 types of rocks. Your teacher Prince have already tackled the first type of rock, which is the igneous rock. And now we will going to talk about sedimentary rock and metamorphic rock. All sedimentary rocks are formed through 5 basic steps, and these are weathering, erosion, deposition, compaction, and lithification. And let's look at each of these steps individually. So the first step is weathering. This is the breaking apart of larger rock into a smaller pieces and eventually be reformed into sedimentary rock. So weathering takes place in a lot of ways. For example, wind, water, ice, or gravity, or any other forces that cause rock to break into smaller pieces. So the second step is erosion. Erosion is the movement or transportation of the pieces of rock or classes of rock. Again, there are a lot of ways where rock can be moved or can be transported, such as wind, water, ice, gravity, and these two steps, weathering and erosion, often takes place at the same time. And the next step, or the third step, is the process of forming a sedimentary rock called deposition. Each rock that's moving or being transported must come to a stop. This happens in this deposition. There is where classes or pieces of rock came to rest on a surface. For example, it can happen on a riverbed, at the bottom of the rock slide, or where a river let out into the ocean. Anytime a rock came to rest or settle in the surface is known as deposition. Over the years, as more and more rocks or clumps of rocks are being deposited, we get our fourth step, which is compaction. Compactions happen when layers of rocks piled up the rocks underneath and become compacted, making the rock closer and closer together. These remove a lot of spaces that between these rocks have. And this is done as more and more weights is layered on the top of the rocks. And this will lead us to our fifth and final step, which is lithification. Lithification takes place as mineral dissolved in water slip into the spaces between the rocks. These minerals work to cement or glue these classes together. The process of cementing or gluing the rocks pieces together is what we call lithification. That's describe the five processes required to make any sedimentary rock. Again, we have weathering, erosion, deposition, compaction, and lithification. And now we will talk about metamorphic rock. Metamorphic rock are one of the 3 types of rocks, and the others are sedimentary rock, igneous rock that are previously being discussed. Each this type of rocks are formed in different way, in their own way, and can be identified by their unique characteristics. And now we will talk about metamorphic rocks. Metamorphic rocks are formed when existing rocks experience extreme heat and extreme pressure. This word metamorphic is very similar to the word metamorphosis, which means to change the form or structure or the characteristic of an object. When we're dealing with metamorphic rocks, we have changed the original structure or form of the rock into a metamorphic rock. We can take a sedimentary rock or igneous rock or even a metamorphic rock and change it into another metamorphic rock. Again, this is done through the extreme heat and extreme pressure. The original rock is known as the photolith, and the extreme heat and pressure changed the physical structure and chemical makeup of the rock until it's become this metamorphic rock. Metamorphic rock can be formed deep in the earth crust or through plate tectonics, such as collisions, or also through magma intrusion into existing rock. All of these processes increase the heat or the pressure to change the existing rock into a metamorphic rock. These are the two main classifications of metamorphism. These are the contact metamorphism and the regional metamorphism. Contact metamorphism. This is a localized type of metamorphism that takes place near igneous intrusion, such as dikes or batholiths. The high temperature of the igneous intrusion can cause contact metamorphism of the native rock near the edge of the intrusion. Contact metamorphism usually have the higher temperature but lower pressure than the regional metamorphism. Regional metamorphism takes place over large areas, whereas contact metamorphism again is usually localized or into smaller areas. Example of where regional metamorphism might take place could be at the base of the mountain where two tectonic plates are collided. With this situation, extreme heat or extreme pressure are being while regional metamorphism takes place over a large areas. Example where regional metamorphism takes place is at the base of the mountain where two tectonic plates are collided. In this situation, there is extreme temperature and extreme pressure. One key classifications of a metamorphic rock is what we know as foliation. This is show up as a layering in some rocks, and this is where an existing rock has been squished or elongated along a particular axis and can be shown up at a different color bands. We will often identify a metamorphic rock as either foliated or non-foliated. Let's take a look at a few examples of a metamorphic rock. We will identify their name of the rock and the photolith or the rock that is originally started. First, let's take a look at the gneiss. This is a metamorphic rock that typically comes from igneous rocks such as granite. And as you can see in this example, the crystal of the igneous rocks has been elongated to show foliation. The second example is the slate. This is a metamorphic rock that is formed when we add heat and pressure in the sedimentary rock of a shale. So that is the end of our discussion on rocks and minerals. Does anyone have a question about the topic? Anyone? None? So I hope you learned a lot from our discussion. But before we end our class, I wanted to know or to test your understanding. We will have a short item quiz. So please click the link that I posted on the chat box. You will have 10 minutes to answer the quiz. For your assignment, I wanted you to explore more about the rock cycle and the 3 types of rocks using the Gizmo website. So log in the Gizmo website using this link. On your screen, you will see the search menu. And type the rock cycle on the search menu and click the launch icon. Screenshot your answer and score and attach it to your paper and submit it to our Google Classroom. Thank you, class. Thank you for participating, and I hope you will do the same in our future classes.